Hello.
Yes, sir, you're audible.
Yes, sir, you're audible. Thank you. So, can we begin? See, I think we had covered time of flight mass analyzer, then the magnetic sector mass analyzer, both single focusing and double focusing, and then the quadrupole. And I think I explained to you the difference between quadrupole mass analyzer and the case of a sector analyzer or a time of flight mass analyzer. And comparison I gave was between a filter and a monochromator like grating, where in case of a filter, you are going to get only one single wavelength coming out, all other wavelengths are absorbed. Whereas in the case of a grating, the wavelengths that are available falling on the grating are dispersed. And therefore, each and every wavelength can be scanned, can be analyzed, can be applied to the sample. Whereas in case of filter, whatever wavelengths are falling on the filter, only one particular band of wavelengths will be allowed to transmit and all other wavelengths will be absorbed. Exactly the same thing is the difference between a quadrupole and a sector analyzer or the time of flight mass analyzer, because in quadrupole mass analyzer, only one M by Z value, ion beam having a particular M by Z value, is allowed to pass through, and it reaches the collector electrode and registers the current. All others either hit the quadrupole or they are deflected and they are not able to reach the slit and the collector electrode, and hence they cannot be analyzed unless you change the experimental conditions. So this situation is something like a filter. Whereas in case of a sector analyzer or in case of a time of flight mass analyzer, whatever M by Z values you have, beams with different M by Z values, they are simply dispersed or simply they are separated. And then you can have each and every one of them analyzed because they are separated under the given set of conditions, and you can change one of the parameters and you can analyze the M by Z value and determine the quantitatively how much quantity of that particular M by Z is present in the given sample. In the case of ion trap, you will find that, or the next analyzer also, you will find that it is behaving in a manner or similar to a quadrupole mass analyzer. So an ion trap mass analyzer and the FT mass analyzer, which is the next advance of the ion trap, both are found to behave as filters. They are not separating, they are not dispersing the ion beam. Doing it's something similar to a quadrupole mass analyzer. It is just going to pick up one particular M by Z and all others will get eliminated, whether it is ion trap or the Fourier transform type of mass analyzer. In both the cases, the basic action remains the same, and the basic action is of filtering out and selecting only one particular mass analyzer. One particular M by Z value for the analysis reaching the collector electrode. Now, what exactly is the difference between what you call as a quadrupole mass analyzer and the ion trap? Now, the basic difference between a quadrupole mass analyzer and an ion trap is, as the word trap suggests, what happens in the case of quadrupole mass analyzer? In the case of quadrupole mass analyzer, you are able to select one particular M by Z value. I think we have it. No, it is time of flight. Sorry. One particular M by Z, and that particular M by Z is able to move unchanged to the, as you can see over there, one particular M by Z value is able to move unchanged through the quadrupoles and reach the collector electrode through the slit. And all others get deflected from their path and hence they are eliminated. Now, in the case of a ion trap, why the word trap is used? The answer is very simple. In the case of an ion trap, the ions with a particular M by Z value, they are trapped inside. All the ions with the M by Z value, different M by Z values, they are trapped inside. And then you can select one particular M by Z, and then that will get detected. So it is called as ion trap because you are able to collect and keep the ions in that particular volume or in that particular ring which is being used. So as you can see, there are two types of electrodes. As you can see on the screen, the diagram for the ion trap is there. You can see the two electrodes, the ring electrode and cap electrodes. Now, what is the effect or what exactly is the function of the ring electrodes and of the cap electrodes? Now, they are called as end cap electrodes. I don't know whether it's shown over here. Yes, in the diagram to the extreme right, you can say it is the end cap electrodes which are in the hyperbolic form, and then you have got a ring central electrode which will trap the ions in the form of a ring. What you are getting or what you are seeing on the screen is a plain diagram, but actually what you have is in a three-dimensional space. So the end cap electrodes are the two electrodes of the four poles used in quadrupole. In quadrupole, quadra means four and poles means electrodes. So in quadrupole, you are using four electrodes. Same four electrodes in a different form, in a different design, and in a different geometry are used in the case of an ion trap. You have got two electrodes in the hyperbolic form, as you can see at the upper right corner of the screen. They are called as the end cap electrodes. And you have two electrodes on the side, which will keep the particles in the form of a circular orbit in that particular volume. As you can see over there, the ions have been shown to be trapped or to be confined to that particular region in space between the four electrodes of the quadrupole that you are using. Instead of quadrupole where you have four cylindrical poles or four cylindrical electrodes, in this case you have got the two electrodes which are hyperbolic in shape and two electrodes which are of ring type. And these two electrodes which are hyperbolic and two electrodes which are ring type are able to maintain the ions inside that particular volume as shown over there. It's a flat planar diagram, but actually what you can consider is that the ions are being present in the volume enclosed between them. And just like what you have in a quadrupole, you have got a direct current and you have got an alternating current of radio frequency. The same principle is applied here. As I said, the basic principle is same, only the design, the geometry is, fabrication is different. So you have the end cap electrodes which will have the direct current, and then the ring size electrodes which you have on the sides, they will have an alternating AC current of radio frequency. Because the ions are trapped, are made stationary, or made to follow an orbit in that particular volume, you call it as IT or ion trap mass analyzer. The word trap is used because ions are trapped. They are confined in the volume which has been shown in the right upper corner of your diagram. That is where the ions are confined in that particular volume. And this confinement is possible because of the geometry of the electrodes that you are using. The hyperbolic end cap electrode, as you have seen over there, and central ring size electrodes which are there in between. And as a result of these two electrodes, one having a DC and other having an alternating current, you can trap ions inside the electrode system. And you may wonder from where the ions are coming in. As you can see on the left side of the diagram, the left hand side diagram, you can see entrance of the ions into the system, or I think the next one also will show you the entrance of the ions into the system. So as the name implies, ion trap mass spectrometer systems trap the generated ions before separating them by mass. Its action is similar to that of a quadrupole analyzer. Now, why you say that the action is similar to that of a quadrupole analyzer? The answer is simple. Its action is similar to that of a quadrupole analyzer because all the ions are trapped in that particular volume by means of the two electrodes, the end cap electrodes and the ring size electrodes, one applied with direct current, another applied with an alternating current. And those ions, once they are trapped, they will have different M by Z values. They are confined to that volume. They are confined to that region. And then you can select one M by Z by changing the parameter, by changing the conditions under which the ions are trapped. Now the question is, how will you alter or how will you change the conditions so that one of the ions with a particular M by Z value, set of ions with a particular M by Z value, will get destabilized and will be able to reach out of that confined volume, will come out and will be able to reach the electrode to register the current. That is how it should happen. Otherwise, just confining the ions with different M by Z in a volume has no meaning. So it's like collecting the ions first in a small volume, and that's why it is called as ion trap. And after the ions are collected, you select one particular M by Z out of all those collected ions. So ions with that M by Z will be able to come out of that ion trap and they will be able to reach the electrode. Now the question is, how can this be done? Under a given set of conditions, you have trapped ions, you have confined the ions, and they are moving maybe in a circular path or around orbit in between the volume of the volume enclosed between the two electrodes or the two pairs of electrodes, if I'm more correct. One is the end cap and the other one is the ring size electrodes. Now, if you want to make one particular ion of particular M by Z to leave that orbit, to leave that path in which it is moving in that confined volume, then you have to change the parameters, then you have to change the conditions. And what conditions you can change? The only options that you are available are the direct electric current, which is applied to the end cap electrodes, or the alternating current, which is applied to the ring size electrode in between. So you can have only one of those two alternatives available, which can be altered or which can be changed, so that ions with one particular M by Z will have their orbit destabilized, and they will come out of that and reach the collector electrode. So only thing that you can change is either the direct electric field or the alternating electric field, because there's nothing else which is there to change to make the ion get destabilized with one particular M by Z value, come out of that volume and reach the electrode. So like a quadrupole analyzer, only the required ion will reach the collector electrode and all other ions will be eliminated. It filters the unwanted ions and only the required ion will be able to reach the electrode. So that's why its action is exactly similar to the action of a quadrupole mass analyzer. Only the geometry and therefore the mode of selection is going to be different. In the case of quadrupole mass analyzer, there is no collection. You have the ion beam coming in with different M by Z values. You have set the experimental conditions. So under those experimental conditions, only one particular set of ions with a particular value of M by Z will move undisturbed in that channel created by the four electrodes or the two pairs of electrodes or the four quadrupoles, as you can say. And that beam of ions with that M by Z value will reach the collector electrode and all other ions will get eliminated. Here, because of the geometry, the situation is different. You are confining the ions to a volume and then changing the conditions so that one particular ion with a particular M by Z will come out of that volume and reach the collector electrode. So that is the basic difference in the operation. Otherwise, the basic principle remains the same, that you are selecting one set of ions with a particular value of M by Z which should reach the collector electrode. In this case, you are confining and stabilizing the ions in a small volume and then doing the selection. In the case of a quadrupole mass analyzer, the ion beam is continuously moving, and therefore, as the ion beam is continuously moving, only one particular M by Z will be able to move through the channel undeflected, unchanged in its path, and it will reach the collector electrode. All others will get deflected and will not reach. So here, that is again a basic difference which I want you to understand. In case of a quadrupole mass analyzer, what will happen? I have set the conditions of the field, the direct field and the alternating radio frequency current. And therefore, as long as I have the supply of ion beam, ions with a particular value of M by Z will be moving undeflected and reaching the collector electrode. Correct? But all other ions will get deflected. So this is what we call as a continuous supply. The supply is continuous. because as long as the ion beam is there and as long as the ion beam is entering the system of the four quadrupoles or the channels created by the four quadrupoles, there will be continuous supply of ions of a given m by z value to the collector electrode. In this case, this is not the situation. What happens in this case? You are collecting the ions and confining them into a particular volume. And out of that, you are selecting one particular m by z to reach the electrode. So all the ions are confined. So there is no continuous supply, no continuous flow of ions into the ion trap. You have the ion beam and the ions are received, they are collected and confined to that small volume. And from that, you are going to pick up one particular m by z by changing the experimental conditions. And as I said, the only experimental conditions that you can have is the change in the strength of the fields, the direct or the alternating current, which by means of which the movement or the orbital motion of the ion will get disturbed, and one particular ion with the m by z value will be able to reach the collector electrode. So in this situation, you will not have what you can call as the continuous flow of m by z of a particular m by z value reaching the electrode as you get in case of a quadrupole. So this will be what you call as a pulsed response. The response will not be continuous. Response will be pulsed. That is, once you pick up one particular m by z, then that will reach the collector electrode and register the current. If you want the same m by z again, then you'll have to go back to the ion beam, ion stream, collect the ions again, bring them into the trap, confine them to the volume of the ion trap, and then do the selection or then do the picking up of one particular m by z by changing the conditions. So that is why in case of a quadrupole, once you have set the conditions of the fields, one particular m by z will move through that channel undisturbed and will go to the electrode. It is not the case over here. You are collecting the ions. So once you change the conditions, the ions which are being collected, out of that, all those ions with the one particular m by z value will go to the collector electrode, register current, and after that there won't be any current at all. No further supply, because whatever ions you had collected in that ion trap, in that small volume, all the ions with that particular m by z value have already reached the electrode, registered themselves, got discharged, and registered the current. So once this happens, it's going to be what you can call as peak form. And if you want a repetition, you'll have to again go back to the ion beam, collect the ions, bring them to the ion trap, and again change the conditions so that that particular ion with m by z will go to the collector electrode. It is something like, if you want a similarity or analogy, it is something like the difference between what you can call as a flame atomizer and what you call as an electrothermal atomizer. What happens in case of a flame atomizer? You are continuously sucking the solution through that Venturi reaction, through the capillary, by means of the Venturi reaction, and then the solution is continuously splurged into the flame. It is continuously entering the flame. So as long as the solution is being sucked in the capillary, nebulized, and transferred to the flame, you are going to get continuous response, because atoms will get continuously formed in the flame and they will continue to absorb. Whereas when you go to an electrothermal atomizer, you are starting with a given amount. That amount is vaporized, atomized, and then the atoms will be in the path of the beam and they will absorb, and then the response will be registered. But there is no continuous flow in that case, because whatever atoms have been formed from the sample after vaporization and atomization, all of them have absorbed the radiation and given their response, or have given the corresponding current for the photomultiplier tube. So once that is registered, no fresh current or no fresh signal from the sample will be possible, because all the sample have been exhausted. It has been vaporized, atomized, and whatever atoms you have in that vapor, all of them have absorbed the radiation and the signal has been registered with the PMT. So if you want a fresh value for the absorbance or the signal to the PMT, then you have to again start with the sample again and then vaporize, atomize, and again record the absorbance. So this is something exactly similar to that what happens in an electrothermal atomizer. There is no continuous signal in an electrothermal atomizer, whereas in case of a flame atomizer, there is a continuous signal. So same difference is existing between a quadrupole and an ion trap. Quadrupole will always give you a continuous signal, whereas an ion trap will give you a pulse signal, because whatever ions have been trapped, all those ions with that particular M by Z value will reach the electrode and the current will be registered. So after that, there won't be any further current possible, because whatever ions were collected and trapped, out of that, those who would have to be reaching the electrode, they have reached and registered the current. So that is exactly the difference between the quadrupole and the ion trap mass analyzer. Okay, the stabilization and destabilization of the ions is brought about by careful operation of the alternating current and the magnetic field as well. So you are stabilizing, first you are stabilizing it. And the stabilization is such that all ions with different M by Z values will remain in that volume, will remain in that particular space, and may be forming what you can call as a round path. Now the question that is how we will make them move round or follow a circular path or an orbital path. An electric field will not do it, because it will simply bend, and the ions will go in one direction or the other depending on the bending that the electric field causes. So to keep them in that circular path or in the round orbit, what is done is you are applying a magnetic field which will deflect, and just like in a cyclotron, the application of the magnetic field keeps the ion beam in a semicircular path in the D. Same way in this case, what you will do is you will apply the magnetic field so that the ion beams will follow a circular path or will remain in the particular orbit. By a combination of the electric and the magnetic field, the ions are trapped inside the mass analyzer. That I just explained to you, that the electric field will bring the ions into that volume, and the magnetic field will trap them or make them move in circular orbit because of the action of the magnetic field on the ions, and the orbits will be of different paths. The path difference will be there, or the path lengths will be different for different ions with different M by Z. Because those who have done the cyclotron will realize this, that the path length depends on the M by Z value, and it will be different for different M by Z values. Therefore, the magnetic field will stabilize it, and the electric field will bring the ions into the volume, confining them in that particular volume, and stabilization of their orbit. Because why the magnetic field is needed? Why you need the magnetic field to make them stabilize in an orbit or in a circular motion? The reason is, if you don't do that and simply the ions are trapped in that particular volume, there will be collision amongst the ions. There may be dissociation, there may be association, there may be further fragmentation. All those points or things can happen because you are leaving the ions in that small volume, and they have got very good velocities because of the acceleration. And therefore, there will be all sorts of reactions like combination, dissociation, fragmentation may be possible. There won't be neutralization because all of them are carrying the same type of charge. So neutralization will not be there, but there may be association, there may be further fragmentation which may occur or which may take place. So to avoid that, you will use what you call as the magnetic field to make them circular, move in a circular orbit. And that also by different M by Z, the paths of the circular orbits will be different. So there won't be any question of being collision amongst them in that small volume of what we call as the ion trap. Then the second important point is you have to change the conditions. As I said, what are the conditions? The direct field, the alternating field, and now the magnetic field, which has stabilized the orbit. So you have to change those conditions, and the change in the condition has to be such that at a time only one M by Z will have its orbit destabilized, will move from its destabilized circular orbit, and will be able to reach the collector electrode. So when will it reach the collector electrode? It will reach the collector electrode only when its circular orbit, destabilization of its circular orbit will be brought about by changing the conditions. And the conditions are two types of fields we are using: the direct current, the alternating current, and the magnetic field. And mainly it should be the alternating current and the magnetic field which should be altered to disturb the ions from its circular path. Now, one more point which I want you to understand is that an electric field which involves a moving charge is also capable of producing a magnetic field of its own. I hope you're aware of this point. So when you have an electric field which is oscillating, it is having a radio frequency oscillator, there will be an oscillating magnetic field as well because of the electric field that you are applying. Okay. So the design of the quadrupole is changed. It uses a static DC current and an oscillating radio frequency alternating field. The design of the quadrupole is changed. The four rods of the quadrupole are replaced with two hyperbolic metal electrodes known as the end cap electrodes facing each other. That's what we had shown in the case of the diagram, as you can see over here. These two are what you call as the end cap electrodes, and the two are the what you call as the ring-sized electrodes. A ring-sized electrode is placed between the two end cap electrodes. Again, I can show the diagram. You can see that these are the end caps electrodes and these are the two ring-sized electrodes. And this is the volume in which the ion beam will be confined or trapped, and hence the name the ion trap mass analyzer. A ring-sized electrode is placed between the two end cap electrodes. Ions are trapped in a circular flight path based on the applied electric field. The ions are introduced in a pulse mode. They are all temporarily trapped inside the electrode. In this state, the ions with varying mass are experiencing stable oscillation. Subsequently, to detect a specific ion, the high frequency voltage is gradually increased while keeping the direct voltage to almost zero. So what does this mean? You are collecting the ions. The ions are trapped in a circular flight path based on the applied electric field. The ions are introduced in a pulse mode. They are all temporarily trapped inside that volume. Now, the electric field, as I said, you will have an electric field which is oscillating. It is a radio frequency electric field, and that will also produce what you call as an oscillating magnetic field. So the oscillating magnetic field will keep the ions in circular path, maybe in opposite directions, as the oscillation frequency of that particular electric field changes. Subsequently, to detect a specific ion, so when I want one particular ion of one particular m by z value, what I should do? All of them are confined in that volume. They are moving in orbital path or semicircular path because of the electric field producing a oscillating or changing magnetic field. So to detect a specific ion, this particular condition, which has stabilized all the ions with different m by z, this should be changed. And this is done by increasing the high frequency voltage so that as the voltage increases, the velocity of the ion will increase. And under that condition, with a set voltage which is applied, only one particular m by z value velocity with one particular m by z value will be able to reach the collector electrode. Consequently, 1 minute, I think, while keeping the direct current. So how is the main operation? The main operation is done by changing the electric field, which is oscillating. It is a radio frequency electric field. So by changing that value, you will change the oscillating magnetic field as well. And because that changes, the electric field will change the velocity. If you are keeping a constant electric field, so velocity will remain constant because ions are charged. And with a one particular m by z value, the velocity will also remain constant because what is the energy given? Energy given in an electric field is V into E, and that is equal to 1/2 mv square. So one particular set of ions with a particular m value will have a fixed velocity V in that particular strength of the electric field. What I wanted to understand is that the electric field is oscillating, but its value or its magnitude is not changing. It is an alternating current. So the frequency of the alternating current is radio frequency, but whatever alternating current voltage that you apply, that is not changing. And it is the voltage that is applied to the positively charged ions that will decide what is going to be the velocity. Because the energy input is V into E. V is the applied voltage, E is the charge on the ion, or Z, V into Z you can say. Z is the charge on the ion, V is the applied voltage. That is equal to 1 half mv square. Now for m by Z, it will be V upon V square. Capital V upon V square. Or V square, the velocity square, is going to be what? It is going to be m by 2z into V, if you rearrange the equation. So all the ions with one particular m by z, as long as V is fixed, is going to have the same value of V. And this value of V for a given voltage is going to be different for different ions with different m by z. Because your equation is the velocity V is equal to, what will be the equation? M upon 2z into capital V, that is the applied voltage. So m by z, if it is common, V is common, the velocity will be same. If m by z is different, V is common, the velocity will be different. So when you are trapping the ions in the ion trap, ions with different m by z values will have different velocities. Now you change the strength of the electric field. That's what it says. The alternating electric field is increased. So you change the strength of the electric field. So what I'm trying to repeat and emphasize again and again is that alternating AC current is of constant voltage V. What is changing is the rate at which the polarity changes, that is the frequency of the alternating current. And that frequency of the alternating current doesn't affect the energy input, because the energy input is dependent on the voltage and not on the frequency. So as long as your voltage is constant, even though it is an AC current, it's going to have the same energy input, and therefore the velocity for a given m by z will remain constant. Moment you change that, all the velocities will change. Different ions with different m by z values will now have a new set of velocities, because you have changed the applied voltage. But that is arranged in such a way that only one set of ions with an m by z value will not be able to move in that particular field, in that particular volume, and that's why they will come out. How they will come out, I think those who have done the cyclotron, they will understand that if the radius of the path is more than the radius of the D that is used in the cyclotron, the ion beam comes out, because it no longer is able to move in that D, because its radius of the path is more than the radius of the D. Something similar happens over here. The ions have changed the velocities. So as the velocity changes, the radius of their orbit will change. And for a particular m by z set ions, the velocity will be such that the radius of the path will be greater than the volume that has been enclosed in the ion trap. So they can no longer move over there. They will come out and they will reach the collector electrode. Is this point clear? So that is how the ion trap will operate, or ion trap will function. I hope I have made the entire operation clear and how it is different from what you get in the quadrupole. In one way, operation wise, how it is different: there is a continuous signal, here it will be a pulsed signal there, but the basic principle in both the cases is same, and it is filtering out all other ions and picking up only one set of ions with a common m by z value. Okay, so consequently they cannot perform selected ion monitoring, transitions and measurements for transmission type of MS. Furthermore, I will just explain, I'll read and then we can explain to you. Furthermore, they operate by pulse mode, that I already explained, and only a limited quantity of ions can be trapped, resulting in a narrower dynamic range than the quadrupole MS system. Because you have got a fixed quantity of ions trapped in the volume. So that's why there is a pulse mode, and a limited quantity of ions will be able to reach the given collector electrode. First of all, you have a fixed quantity of ions in the ion trap, and out of that, only a limited quantity of ions will have a particular n by z, which can be picked up, and then those ions will be able to reach the electrode. So, moment all those ions in the ion trap with that m by z are exhausted, your signal will stop. That's what it means. However, all trapped ions are detected in the ion trap mass spectrometer. This provides high sensitivity in scanning analysis than quadrupole. So, what exactly it means? If you have got your trapped ions and they have got different m by z values. So, you select one particular condition. So, ion with one m by z value will be tossed out of their orbit because their radius is more than the radius of the ion trap volume. They will come out and they will reach the collector electrode and they will produce a current. All this will be in a pulse form because all the ions of that m by z which are trapped in that particular ion trap, they will come out, they will reach the electrode and they will register a current, and you will get a peak for that particular m by z in the mass spectrometer. Once that is over, the signal will stop because all the ions with that m by z value which were trapped in the ion trap, they have been discharged. They have been already reaching the electrode. They have been discharged, or the charge on them is removed. They have registered the current, and the current of the signal will come to zero. Now, once this happens, what you can do? You can change now the conditions of the electric field so that another set of ions with a different m by z value will be able to get disturbed from the orbit, will have an orbit path more than the radius of the volume of the ion trap, and that will come out, reach the collector electrode, get registered, get discharged, get deposited, register the current, and produce a peak. So you can go on doing this till all the m by z of different ions with different m by z in that ion trap which has been collected have been utilized. So scanning becomes possible. That you can go on changing the conditions till the ion trap ions are exhausted and all of them have been reaching the collector electrode, getting deposited and registering the current. Is this point clear? So it acts as a scanner, collect the ions, and then one by one it picks up ions of a particular m by z, takes them out to the collector electrode by changing the electrostatic field, and registers the signal. Once that is over, again the condition can be changed so that another set of ions with a different m by z, they come out of the ion trap volume because their path becomes more than the volume radius, and then they will get registered and produce a signal. So like that, what you can do is you can get or scan all ions with different m by z values which have been trapped inside that ion trap. So that is why it is said, as it says over there, in the furthermore, the operation pulse mode and only a limited quantity of ions can be trapped, resulting in a narrow dynamic range that quadrupole mass system. However, all trapped ions are detected in the ion trap mass spectrometer. This provides higher sensitivity in scanning analysis than quadrupole models. Because in quadrupole, under the given conditions of operation, only one m by z comes out. So if you are selecting one particular m by z, you are interested only in one particular m by z, then what happens? Then you choose a quadrupole, set the conditions. So you'll always get that m by z reaching the electrode and registering the current and giving the peak. So if you want to study a set of one m by z values only, then the quadrupole mass analyzer is obviously preferred. Again, you can bring out the similarities and differences in the operation. If I want to record the spectrum of a compound, what I do is I scan the entire possible wavelengths, go on changing the wavelengths from the lowest possible value to the highest possible value, and record the response of the sample for all those wavelengths, so that the collection of all that will result or will give me what we call as the spectrum of that compound. So how is the spectrum recorded? By scanning, choosing, applying all the possible wavelengths in that region from the lowest to the highest and recording the response of the sample for each of the wavelengths that you have chosen, compiling them together. That will result in what we call as the spectrum of the compound in the given wavelength region. So that is exactly what ion trap does. It confines the ions and then it picks up ions with different M by Z values one by one and registers the response for them. So as it is possible to change the conditions and it is possible to make sure that all the ions which are there with different M by Z values are able to get registered into the collector electrode under different conditions and register the current, register the peak. So just like you can scan all the wavelengths and record the spectrum, you can change the conditions and you will be able to record all possible M by Z values that are obtained in that ion beam which has been collected in the ion trap. Whereas in quadrupole mass analyzer, what happens is you are setting the conditions. So obviously, it is like setting the wavelength for a measurement. For example, if you want to determine amount of a particular substance, what you do is you choose the maximum wavelength at which the absorbance is maximum, set the instrument for that wavelength, and measure the absorbance, and then from the calibration curve you can find out what is the amount. So a quadrupole mass analyzer works in a similar manner because I have set the conditions. So only one particular M by Z will be able to reach the electrode and register the current. So if I use different samples, then all those different samples, if they have that particular M by Z as the fragment form in the form of the ion beam, then it will register its response. So it is like measurement being done at one particular wavelength. In quadrupole, it is the measurement done for one particular M by Z value. Whereas in the case of ion trap, it is like scanning all the possible wavelengths from lowest to the highest and compiling it together to give you the spectrum of the compound. So here also you scan all the possible M by Z values from the lowest to the highest, compile them together, their response together, and you will get what is called as the spectrum, mass spectrum, with the possible limits of the lower M by Z to the highest possible M by Z value. That is how the difference exists between the ion trap and what we call as the quadrupole. In addition, it enables the trapping of a specific ion, fragmentation of it, and then trapping a specific product for further fragmentation and so forth. Therefore, ITMS is considered as a mass spectrometer specialized for elucidation of the fragments and structural determination of large molecules. Now, how it is possible? You can understand that 1 M by Z is picked up and it reaches the collector electrode and registers the current. Now what it says is that that particular M by Z can be selected, can be fragmented, and those fragments can be studied. Now how will this be possible? Obviously, this will not be possible in one single instrument. I cannot use one ion trap and say that I have one particular M by Z value, ion coming out, and then it is getting further fragmented, and I'm studying the fragments produced. So if you want this type of situation where you are concentrating on one M by Z and then fragmenting it, finding out the M by Z for the fragments produced, and then coming back to the original M by Z and into the original molecule. Now this type of analysis will be possible only in the cases where the original molecule is very large and therefore is able to get fragmented at multiple stages. Now, if you want this type of analysis to be done, then one single ion trap and one single mass spectrometer will not work. What you will have to do is what is called as the tandem mass spectrometry, where mass spectrometers are arranged one after the other. So if I want to analyze one particular M by Z, what will I do? I will select that M by Z, pick it out of the ion trap, let it allow it to come out of the ion trap by changing the conditions, by setting one particular set of the correct field conditions. And instead of that M by Z ions reaching a collector electrode, I will allow them to get into another mass spectrometer where further fragmentation and further ionization will be possible. So if you are talking about studying a particular M by Z in one single IT mass spectrometer, it will not be possible to fragment it and then study the fragments as well. You can pick up one M by Z and instead of making it reaching the collector electrode, you can transfer it to another mass spectrometer where it can undergo ionization, further fragmentation, further energization, and then study it. So this type of analysis will be possible in what we call as a tandem mass spectrometry or MS raised to N. So one mass spectrometer, second mass spectrometer, third mass spectrometer, and so on. That's why it is called as MS raised to N. Any number of mass spectrometers you can collect, bring them aligned together, and then the analysis of the fragment can be done. So if you want to study a one particular fragment, but one particular M by Z, and then allow it to further fragmentation, in single ion trap mass analyzer, it will not be possible. For that, you will have to collect that particular M by Z and transfer it to another mass spectrometer for the fragmentation study. And this is just another way of representing the same thing. The electrodes, the ring size, and how the ions will come out and will get discharged under unstable oscillations at the collector electrode. What is FTICR? That is the last mass analyzer which we are going to discuss. So what is FTICR? FT, all of you are familiar. What is FT? FT is Fourier transform. ICR, it is, what is ICR? Ion cyclotron resonance mass analyzer. FTICR is Fourier transform ion cyclotron resonance mass analyzer. Now, what exactly is the basic feature of a Fourier transform analysis? Whether it is FTIR, whether it is FTNMR, or whether it is FT in this particular case, what is the basic feature of a Fourier transform? Can anybody tell me? Yes. What is the basic feature? When you say it is a Fourier transform which is being used? Anybody? All of you have studied FTIR, if not FTNMR. You have definitely studied FTIR. So what is the basic difference? I'll put the same question in a different way. What is the basic difference between a regular IR and an FTIR? Can anybody tell me that? That will also suffice. Application-wise or operation-wise, what is the basic difference between a regular infrared spectrometer and a Fourier transform infrared spectrometer? Yes, nobody knows or nobody wants to answer. What is the case?
Sir, it is an interconversion of domains of frequency and distance.
Yes, exactly. So what is the interconversion? Can you tell me? You are right. What you said interconversion. Fine. So what is the domain in which the
FTR we convert time zone?
What is the Fourier transform measurement is done in which domain? You have answered it. Yes.
So time domain is converted into
exactly.
frequency domain in FTR.
Fourier transform measurement is done in time domain. Normal IR spectrometer, when it responds, its domain of measurement is wavelength. You are applying different wavelengths and getting the response from the sample for different wavelengths. So domain of measurement is wavelength in the normal IR. In all Fourier transforms, the domain of measurement is obviously time. And then it is the transform. So the time domain collection data collected in time domain, whether it is FTIR, FTNMR, or even in this case, whatever data is collected in the time domain, that data is converted to the respective domain. In case of FTIR, the domain is wavelength. So the domain of measurement is time, and the Fourier transform converts that from time domain to wavelength domain. When you do FTNMR, the measurement domain is time. What is the domain in which it is converted? You will come to know when you do FTNMR. I think it is there in one of the units, maybe this term or maybe the next term. Same way here, the domain of measurement is time, and then it is converted into the regular domain of current. And why resonance? We'll come to that point also. It is Fourier transform, ion cyclotron resonance. So why it is resonance and why it is ion cyclotron, that we will take up. Similar to the Fourier transform instruments, the FT mass spectrometers also possess the same advantages of increased sensitivity, less scan time, better signal to noise ratio, and a high resolving power. All of you are familiar. These are the basic advantages of an FT instrument. For example, an IR may take up several minutes to record from one wavelength, from the lowest to the highest wavelength. Whereas if you use FT in the same time domain, or 1/10 or 1/100th of that time domain, you can record a number of spectra and convert them. So one of the advantage is less scan time, more sensitivity, better sensitivity, and signal to noise ratio will be going closely with one another, and a higher resolving power, that is separation between two adjacent wavelengths in case of FTIR. It uses, and in this case, obviously it is going to be separation between two adjacent masses. It uses an ion trap and takes advantage of the ion cyclotron resonance phenomenon. So that's why it is called as FTICR. It is a Fourier transform which is used, and it takes advantage of what is an ion cyclotron resonance phenomenon. What exactly is a cyclotron? Yes. What is a cyclotron? At least those who are from physical, they have done cyclotron, so they should be able to answer. If not others. What is a cyclotron?
It is a type of a particle accelerator.
Yes. And what happens in a cyclotron? Why it's a similarity between this and a cyclotron. That's why we call it an ion cyclotron resonance. So what happens in a cyclotron? In a cyclotron, you have got a magnetic field applied in a form of a semicircular half disc, which you call as D. The charged particle is accelerated between the two such semicircular Ds. They are half circular Ds, and there is a gap between the two, and that gap is covered with an electric field. So the Ds are connected to the two terminals of an electric field, and there is a magnetic field applied over both the Ds. So the ion gets accelerated because of the electric field. It moves inside the D, and inside the D it is under the magnetic field, so it follows a semicircular path. When it comes out, the polarity of the other D changes. It gets accelerated toward that D because there is an electric field between the two Ds, and it enters the second D. Again, when it enters the second D, it is under the influence of a magnetic field. It follows the semicircular path, and so on. That is how the cyclotron works. So the point here is the resonance part. That's what I'm coming to, and then we can stop. In a cyclotron, the charged ions enter the magnetic field and move in a circular path of radius r in a plane perpendicular to the direction of the applied magnetic field. The radius of this part depends on the applied magnetic field. The angular frequency of movement in this circular path can be obtained in terms of the field strength and the charge and the m value. That expression is there, dZe upon m, where That is the frequency, angular velocity of motion for the semicircular path of the ions. And it is BZE upon M. B is the magnetic field. Z is the Z. It should not be BZ. It should be upon M. E is the charge and M is the mass. That you can refer to any cyclotron textbook and you will get this particular expression. The angular velocity is inversely proportional to the M/Z value. Increase in the velocity will get reflected in the increased radius of the path of the ion beam. That's what happens. When the ion gets charged in the electric field, its velocity increases, it's energized, and that increased velocity is reflected in increased semicircular path of its motion inside the beam. An ion trapped in a circular path can absorb energy. This is what is called as cyclotron resonance phenomenon. So what we are now coming up to is what is called as ion cyclotron resonance phenomenon. An ion trapped in a circular path can absorb energy from the electric field and increase its velocity if frequency of the alternating current is same as the frequency of rotation of the ion. Why is it called as resonance? Always you call it as resonance when two things are coinciding, having the same magnitude, the same value. That's why you call it as nuclear magnetic resonance. By the way, you can think about what happens in a nuclear magnetic resonance spectroscopy, why you call it as resonance. So in that case, the ions are moving in a circular path in a magnetic field. And if you have an electric field applied to that at the same time, then the absorption of energy from the electric field will be possible if and only if the frequency of the oscillating electric field or the alternating current electric field is equal to the frequency of rotation of the ion. And what is the frequency of rotation of the ion? It will be its linear velocity divided by r. That is going to be angular velocity is going to be omega, which is r. They will decide its frequency of rotation. So what will be frequency of oscillation is 2 pi upon omega. Frequency of rotation will be omega upon 2 pi. I'm repeating again what I'm saying. The angular velocity of rotational motion is v upon r, where v is the linear velocity and r is the radius of the angular path. Now, the angular velocity will decide the time for one oscillation. So one oscillation will complete 360 degrees or 2 pi radians. So the time for one oscillation will be 2 pi upon the angular velocity. So 2 pi upon omega. Correct? So the frequency will be omega upon 2 pi. So what it says is that the frequency of this rotation of the ion should match with the frequency of the alternating electric field. If these two match, then the ions will absorb energy from the alternating electric field. And what happens if they absorb energy from the alternating electric field? They will get accelerated. Their velocity will change. The absorption of energy, I'll take just another 1 or 2 minutes. Sana, are you there? Sana? Are you there? Abhishek, who is going to take the next class? Or is there
are no lecture after this.
Pardon?
So there are no lectures after this.
Okay, so then I can continue and complete it another 5 minutes. I was worried if somebody else is going to take them, there will be problem. Okay, so what we are talking about is the frequency of rotation of the ion matching with the frequency of the alternating current that you are applying. So when these two match, it is called as the resonance. That's why the name ICR, ion cyclotron resonance. Resonance because the two frequencies are matching. The absorption of energy from the electric field will occur. And this absorption of energy from the electric field will increase the velocity of the ion. Obviously, absorption of energy will change the kinetic energy. The velocity will increase. And the velocity of the ion beam with a particular value of m by z. Now, why this? Because the angular velocity will depend on m by z. And therefore, this particular matching of the frequency of rotation and the frequency of the alternating current will be possible for only one set of ions with a particular value of m by z. I repeat again, the matching of two frequencies is there, the frequency of rotation of the ion and the frequency of the alternating current electric field which is applied. The two frequencies, if they are equal, then energy will be absorbed. Now, this particular situation will be possible with only one set of ions with one particular m by z value, because angular velocity depends on m by z. So the frequency of rotation depends on m by z. So this condition of matching of two frequencies will be possible only for one set of ions with one particular m by z value. This will change the radius of the circular path and hence the orbital moment of the ion. For ion beam with a different m by z value, the resonance frequency of electric field will be different, and hence they will remain in the path of the field and the ion will resume the original path. So basically, this process produces what is known as the image current that is found to be exponentially. That's why the image current is measured in the time domain and then converted into the mass domain to give you that particular m by z. The frequency of this image current that will be characteristic of the ion beam with a definite value of m by z. So basically, what is being done? Energy is being absorbed. The velocity will change. It is not that, see, that is what I want to understand. It is not that that particular ion is going to be because of the change in velocity. What it says is that the ion cyclotron resonance phenomena will produce an image current in the circuit because of the increased velocity of the ions with the one particular m by z value. And what we are going to, and this image current distributes exponentially with time. So what one can do is, one can go on changing the frequency of the alternating current. So at one value, it will match with one m by z. Another value, it will match with another m by z. For third value, it will match with a third m by z. So when you are continuously changing the frequency of the alternating current, the matching with different m by z ion beams will become possible. And then respective image currents will be registered in the collector electrode. And this is measurement done under time domain. So we are changing the electric field and measuring the collector electrode current as a function of time, because all Fourier transform measurements are done as a time domain measurement. So all the signals, what is going to happen? As you change the frequency of the alternating current, you will have resonance possible at different frequencies for ions with different m by z values. And moment you get that resonance, you will get an image current in the outer circuit or in the collector electrode circuit. And this image current will be measured by the collector electrode. And this particular changing in the frequency of the alternating current is out over a time period. And correspondingly, the current is measured. And then it can be converted from time domain to the mass domain to give you the mass spectrum. So the magnitude of the AC image current depends on the number of ions in the ion beam. So quantitative analysis is possible. That the magnitude of the image current will be proportional to the concentration of the ions with the constant m by z value. At different applied frequencies, the electric field when different ions will resonate. This quantitative determination becomes possible. The decay of the image current with the time forms what we call as the time domain signal. So this is the diagram. So basically how it happens, you have ions in a circular field like what you have in an ion trap. Then you go on changing the frequency of the alternating current in a given time interval. As you change the frequency of the alternating current in a given time interval, at different changing frequencies, ions with different m by z value will resonate. That means their frequency of rotation and the frequency of the alternating current will match. They will become equal. And when this happens, there will be an image current registered. So when you are making the measurement over a given time domain, say 10 seconds, 1 second, 10 milliseconds, 100 milliseconds, whatever the case is, the frequency of the alternating current is changing rapidly from one value to another, so that all the ions with different M by Z are able to resonate with the applied frequency at one particular time instant, one particular point of time, and all these signals produced, because this entire process is being carried out over a regular time domain, regular time interval, and all these signals, because of the changes in the resonating frequency of the alternating current, you will get all the signals from different M by Z values. The image current is proportional to the amount or concentration of M by Z. So quantitative determination for different M by Z is possible when the signal data collected, signals received in the given time domain are converted into mass domain. And that is how the ICTR works. Okay? Any question, any queries?
Hello, sir.
Yes.
Sir, actually, I had a doubt with the question that you had given for the quiz.
Yeah, no, what I am going to do is I am not assessed. So I will assess and then give you the answers tomorrow.
Okay, sir. Thank you.
Or what are the expected answers for the quiz? I have not gone through all the answers. And I don't think I'm going to give marks. I'm just going to go through and then I'll give the answers. And when I'm giving the answers, I can answer to the queries, whatever way you have answered, how it is wrong or right, or how it can be changed. So that I will do tomorrow because I have not gone through all the answers still. Okay?
Yes, sir.
Any other query? Then we can stop for the day. That will complete all the mass analyzers that we are talking about. So from tomorrow onwards, we will start with interfaces used in LCMS, which work as ionization as well as conversion of the eluent to the mass spectrometer, transferring the sample or solute from the LC to the mass spectrometer. There are two types. I'm going to take up that tomorrow. I'll just say what it is and then stop. There are two types. In one case, the interface works only to transfer the solute to the mass spectrometer. In some other cases, the interface works for the transfer of the solute from the LC to the mass analyzer, to the mass spectrometer, as well as it acts as an ionizer or brings about ionization of the solute. So two different possibilities. In one case, it is ionization and transfer. In some cases, it is only transfer of the solute into the mass spectrometer, and then mass spectrometer will bring about its ionization. So there are the two basic differences. So that we'll talk up and take up from tomorrow. So thank you, and we'll call it a day.